All right, my name is Austin Rowland, and this is my Physics 2 Lab 5 video report on Faraday's Law and magnetic braking. So the purpose of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil, and to model the magnet and tube interaction using a computational model, and then to compare the computational predictions with the observed data. And the results that were gathered from this experiment were that the fall time using the experimental data was 1.56 seconds, while the fall time from the computer model was 1.55 seconds. So this shows that our computational model actually worked pretty well. Some of the fundamental principles used in this experiment were Faraday's law and the Biot-Savart law, and then Newton's third law of motion in relation to the force of the tube on the magnet and the force of the magnet on the tube. So the experimental procedure for this was to record a magnet dropping through the aluminum foil tube, to find entry and exit times to determine total time spent in the tube. Repeat this step with 5 different trials and then find the average time difference between the entry and exit times. So with this experiment, the magnet falls slower due to the change in magnetic flux that creates an opposing force on the magnet, which causes it to fall slower than the acceleration of gravity. And we can see that in this video here, actually. If you watch, it goes a lot slower than gravity normally would. And we'll just look at that one more time. So some of the experimental measurements and data that were collected were the tube length, which was 0.305 meters. The foil width was 0.01 meters. The roll's radius was 0.026 meters. Our magnetic dipole moment was 3.42 am squared. The mass was 0.09 kilograms, and the average fall time of the bar magnet was 1.56 seconds. And here's the computer model for this experiment. So just going through, we can go piece by piece. So we have this section with physical constants here. We have some of these graph initializations. We have this section where we actually go through and start to create the tube of aluminum foil using some of those measurements we had from the experiment. And then we have this step where we go ahead and create the bar magnet, and we have our initial conditions for this experiment. Then we have our function to calculate the magnetic field of a bar magnet, and then this function to calculate magnetic flux. Then we have our simulation loop for visualization, which we will get to see in just a second. And then we have all these calculations that are being performed in that loop, such as, change in flux, the ring's current, and then like the typical B field at each ring, what the magnetic force on the magnet will be, and then calculating net force, and then a velocity and positional update statements as well. So then when we go ahead and we run this code, we can see here that the magnet falls all the way to the bottom, and we can look at our velocity versus time graph here. So there's a little dip at the beginning, and then it goes back up, and then there's another dip off at the end, which we can see. So ways to interpret this computer model and view the results. So the model shows that gravity acts downward while the magnetic force due to the induced current acts upward. When the magnet is in the middle of the aluminum foil tube, magnetic force and gravitational force are equal. The red wing has a clockwise current, while the blue one has a clockwise current, and a change in magnetic flux is downward in this experiment, and therefore induced current is counterclockwise to oppose the change in flux. So what if the resistivity of the conductor were reduced as close to possible as zero? How would the dynamics of the falling magnet change? The induced current would approach becoming infinity as resistivity approaches zero. As the induced current approaches infinity, the force against the magnet's motion, which would be this magnetic force, would increase, and the magnet's velocity would therefore approach zero. And then second question, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? With holes or slots in the tube would have less of an effect on the magnet due to a decreased induced current, and this means that the magnet would fall faster due to less magnetic force acting upon the magnet to oppose its motion. And then just a little fun piece at the end here. We can watch a little magnetic braking trick shot. Kind of cool to see just the effects that you can have when you're able to oppose gravitational force without actually having to touch the object or make any contact with it. All right, thanks for watching.